All right, you folks, can you hear me?
Yes.
Yeah.
We can hear you.
Good.
We can
Let's
hear
wait.
you.
Yeah, let's wait a minute and let's begin. As always, I'm going to ask you if you've understood at various points in the lecture. Please answer yes or whatever the thumbs up so I know I can proceed. I'd like to make sure that students, or at least a majority of the students, have got what I'm trying to convey, just so that we don't lose track. Yeah. All right, let's continue with today's lecture. So here's the recap. We saw that we train a neural network by minimizing a loss, which is the average divergence over a training set. And again, was this loss the actual objective we would like to minimize, or was it something else? What do we actually want to minimize? Guys, just as a recap, I'm sure all of you remember. What did we actually want to minimize? Anybody?
Is it the expected divergence?
That would be the expected divergence. And the loss is just a proxy for it. It's an approximation, right? And we minimize the loss through gradient descent, which are iterative updates against the gradient of the loss with respect to network parameters. When we perform batch updates, which is the actual update rule for the loss, we have to process the entire training data before each update. So instead, we perform incremental updates like stochastic gradient descent or mini batch update. And this can speed it up by performing multiple updates within each iteration. These SGD and mini batch updates can be faster to converge, but they have greater variance and may result in worse estimates. So we also saw that trend algorithms smooth out the variations in incremental update methods by considering long-term trends and gradients. So now again, you guys have been using stochastic gradient descent and mini batch updates in your homework. Is that what you really should be doing, or is that also just some kind of a shortcut or an approximation which you hope will work? What do you think? Is SGD or mini batch updates what we should really be doing? Guys, what's the answer? Mini batch is better? Mini batch is better than what? What should we actually be doing? Anybody?
Can I take a stab at it, Professor?
Pardon me?
I would like to take a stab at it, sir.
Go ahead.
Like, again, forgive me if I'm wrong, but my idea is that the point of like training the model is that we want to like set the parameters such that our hypothesis like curve like comes to like the target curve at every point. But we only know the training point, so we can only set it to the training points. But SGD is even worse. We can only set to it to the training points in the batch. So the most ideal, if we could do it of all the points, the second best is just like gradient descent in general, and the SGD is sort of a compromise. It's faster, but like it doesn't like set the parameters such that the hypothesis is closer to a target at like as many points.
Perfect, right? So what we really want to do is batch updates, where we minimize the average divergence over the entire training set. Instead, we use SGD and mini batch updates as a compromise because that's computationally feasible. And we try to set it so that it comes as close as possible to performing actual batch updates while still being possible. That clear to everybody? Yes, no? That's one yes, right? Okay, so keep that in mind, right? SGD and mini batch are not the real rules. They're just the engineering rules, okay? So moving on, topics for the day, we're going to be talking about generalization, some tricks of the trade, divergences, normalizations, dropout, and a few other tricks. So here's what, first, let's consider these issues, how the convergence could proceed, and how we could make it better one step at a time. Now, the training loss that we minimize is the average divergence over the training set. So the convergence of the gradient descent depends on the divergence function itself. Ideally, the divergence function must have a shape that results in a significant gradient towards the direction of the optima, so that it guides the algorithm to the right solution. So if your divergence function were something of this kind, where the x-axis is a parameter and y is the divergence, this figure to the left is a horrible divergence function. It's not differentiable, and it's got all kinds of ugly local minima. Now, here are two other divergence functions. Both of them have a nice global minimum. But which of the two do you think is better? The orange one or the blue one?
Blue.
The blue. Guys, I may have mentioned this early in class. There is no attendance for today because Zoom takes care of it. So why is the blue better? Anybody? Why is the blue better?
It's a convex.
So it's convex, it's steeper away from the optimum. So the orange one, it's shallow far away and very steep near the minimum. So because the steps that you take are proportional to the derivative, you take tiny steps when you're far away. And then as you approach the minimum, your steps will get larger. And because it's very steep near the optimum, you can actually jump across it and bounce out. Whereas if you had the more bowl-shaped divergence function, then the steps you take are going to be big, far away from the minimum. And then as you approach the minimum, they're going to get smaller and more careful. So the best type of divergence is bowl-shaped. And even so, you don't want it to be too shallow near the optimum, because if it is, then you'll slow down. So a quadratic function is somewhat close to an ideal shape for the loss. So when we train our networks, we have different choices of divergence. We saw that for regression networks, we use the L2 divergence, which is half of the squared norm of the error between the actual and desired outputs of the network as our divergence. You could also use this when you're trying to perform classification, where in a classification network, the final layer is a softmax. However, we saw that a different kind of divergence that we could use is the KL divergence, which for the binary classification case is minus d log y minus 1 minus d log 1 minus y. So this one is going to be infinite when you're infinitely wrong. So if the desired output is 0 and your current output is 1, you're infinitely wrong. So this will become infinite. If the desired output is 1 and the current output is 0, then too this is going to become infinite. The multi-class version of it we saw in an earlier class was this summation over all classes of d log d. This doesn't really matter. This is only computed over the target. The real key component is minus of summation I d log yi, and you can see that if the probability assigned to the correct class is 1, then this becomes 0. And if the probability assigned to the correct class is 0, this becomes infinity. So this too has this property that when you're very wrong, it's in the divergence is infinite. So again, you could also use the quadratic divergence for the classification network instead of the Kullback-Leibler divergence. Yes, you're fine. I'm getting to just that, right? So here is the KL divergence as for a binary classification function where the target output is 0.5, right? If you had a quadratic divergence, the actual divergence function is going to be this orange curve. Observe that it sort of already crosses the boundaries at 0.25. Now, from the looks of it, the quadratic divergence seems nicer because the KL divergence becomes very flat near the optimum, right? So based on this picture, what do you think would be the better divergence if you are, say, at 0.4? If the current estimate is 0.4 and the target is 0.5, which of these two would you want to use? Anybody? L2 looks like the more appropriate one, right? You would be wrong. Why? Because you're looking at the divergence or the derivative of the divergence with respect to the output of the network, which is this y's. But then take a step back. What is the derivative of the divergence with respect to the z's that go into the softmax? Let's plot that. If I plot that, then here is a KL divergence as a function of the z. And here's the KL2 divergence as a function of the z. So now, if you're close to the optimum, which looks better? KL looks better, right? In fact, if I look at a multi-class, so say a two-input function, here this is a scalar input. Here, if I had two inputs, I can't go about two because you can't visualize it. Then if z has two dimensions, or if z is a function of two weights, right? Here is the L2 divergence as a function of the two weights. So let's say I have a logistic or a softmax, and it has two weights, W1 and W2. So then this divergence can be plotted as a function of W1 and W2, right? And this is your sigmoid. And you can see that in the case of the L2, it actually has the flower shape, the shape that we didn't like earlier. Whereas in the case of the KL, it has a nice boat shape, which is why the KL divergence is a better choice for classification networks. Once you go past the final softmax, the KL is actually stays convex for one more layer, whereas the L2 becomes non-convex. This making sense? What about the rest of you guys? Making sense? So you see why the KL is a better choice. So L2 is not convex, while KL is convex with respect to the z values, the logits at the output of the network, which is why we use KL. Now, continuing to think in terms of the z's, regardless of whether you're performing regression or classification, if you use the L2 divergence for regression and the KL divergence for classification, we found that the derivative of the divergence with respect to z in both cases is simply the difference between the actual output of the network, the y, and the desired output of the network. So we are literally always propagating this error backwards. And this is very convenient. You don't have to work out the math. You can just take my word for it. Or you can spend half a page of math and come up to the same solution. So here is my first poll. If I can launch it. There are two questions in the poll, guys. Okay, 10 seconds. All right, let me stop this, right? So, first question, which is the correct answer? Which of the losses is convex with respect to the weights of the final softmax layer? Yeah, right? For the most popular networks, regression network with a linear final layer using L2 loss, or a classification network with softmax layer and cross entropy loss, which is the gradient of the loss with respect to the final z, y minus d, right? So beautiful. You guys got it all. These are the answers. Thank you. So things we've seen in the last class, gradient descent can be sped up by incremental updates. Convergence can be improved using smooth updates. We also see that the choice of divergence affects both the learned network and the results, because it affects how well the network, the gradient descent will converge. Now, here's another problem. We work with mini batches because that's most convenient. Now, what is the assumption that we make when we work with mini batches? There was an implicit assumption that I made when I work with mini batches. What was that? Anybody know this? What was the assumption I made when I worked with mini batches? Anyone, guys? That all mini batches, the distribution of the mini batches mimics the distribution of the actual data itself. So you're expecting that all of the mini batches will roughly have the same distribution. But then, in reality, the different mini batches can be different. In fact, they can be very different. And this is particularly the case when you have deep neural networks where the networks are so nonlinear that data can get moved around a whole lot. So you might have 4 mini batches, and each of the 4 is going to be in a completely different region of the space, which means that the basic assumption you made that every single mini batch is representative of the overall data is going to be wrong. So this is what we call a covariate shift. And this can affect your training very badly. So when you realize this, then what would you want to do with these mini batches? Anybody? This is an open-ended question, but just asking. How would you deal with this? Anybody? Normalize them, right? So what we want to do is to move them all so that they all fall in a standard region of the space. But what is the standard region? Where do we move them to? We have no idea, right? So we're going to follow a two-step process. First, we're going to move every mini batch to the center of the space and normalize them so that they have the same mean and variance. How would one do this? How would one normalize a mini batch so that the mean of the mini batch is now 0 and the variance is 1? How would one do this? Anybody? Z-scaling, right? You have all of the values, let me call this x1, x's now, x1 through xn. You're going to replace each one of these by the x1 minus the mean of the mini batch. So once you do this, the mini batch is centered at 0. Then you're going to divide them by the standard deviation. And then the standard deviation becomes 1. And so all of the mini batches get normalized. And then once you do that, you move the entire lot to a fixed location in space, and the actual location in the space will get learned. So right now, we will see how this works out, right? And so this is what we call batch normalization. It accounts for the statistical variations across many batches in the during training. So okay, 10 seconds, guys. This is easy. All right, let me end the poll. What is the answer? Mini batches, right? And to answer the question of those who said, won't this destroy the overall trends? The answer is yes and no. You're going to be doing this during training deeper in the network. And so long as you ensure that the gradients are correctly computed and account for the transformation that you impose when you perform the normalization, it will learn things properly, right? So the correct answer is mini batches. The trick lies in knowing how to compute the derivatives in a manner that accounts for the normalization. If you don't do that, then yes, you're right. You're going to, whatever you learn is going to be completely inappropriate. So now this batch normalization is a shift adjustment which can be thought of as being performed by a unit. And typically it happens immediately after the computation of the affine function of the inputs to the neuron. So it occurs over here, just before the application of the activation. Although in principle, you could also do it after the activation, but typically this is where it's done, right? And this is performed over mini batches. It's done independently for each unit. So when I speak of batch norm, I'm speaking of what's happened at a specific unit. So let's see what happens at a specific unit. Consider this neuron over here, right? Just this neuron. First, you compute a z, then you put the z through an activation function. So here's what would happen. First, you compute a z, then you put the z through an activation function. But between the two steps, you perform batch normalization. And this batch normalization is performed over the entire mini batch. So you're going to be considering the z's for all of the instances in the mini batch and then be performing this normalization. The way you do it, first, again, the z's are going to have some distribution in the mini batch. You want to move this to be centered at 0. So the first thing that you will do is to compute the mean of the z's in the mini batch and then subtract this mean from every one of the instances. Second, so that centers it. Second, you'll be computing the variance of the mini batch, and from that, the standard deviation. And then you're going to be dividing the z's by the standard deviation. There's a sigma squared plus epsilon. This is just to prevent division by 0. And so this resulting u, which has been z normalized, now is centered at 0 and has a unit variance. Then I want to move this to a new location, but first I want to scale it up because at the new location, it doesn't have to have unit variance anymore. We are trying to mimic the true distribution of the data out there, and there's no necessity that the true distribution has unit variance, right? So first you have to capture this variance, which means that you're going to scale the u by a scaling factor to get the right variance. And then after scaling it, you're going to shift the whole thing to the new position so that it's centered at the correct point. So is this entire process making sense to you guys? First, you compute the mean of the mini batch and the standard deviation. You center the mini batch by subtracting the mean and normalize it by dividing by the standard deviation. That gives you the u. So this first block represents this first process. And then the second block shifts the whole scales and shifts the whole thing to a new location. So Mughal, this is exactly the formula for standard normalization for any distribution, right? So why do we do this? So the point is the z at each for each neuron is a different dimension. We have no idea where it lies, right? And so this is why you do this separately for every neuron. Did that answer your question, Abhishek? And Aditi, how do we know the value of gamma and beta? When we're going to estimate it, right? So again, the point is that you're assuming that the data has some distribution somewhere, right? And so if this were the distribution of the data, you want to move every mini batch to lie right there. And that's what this guy is doing. So that's why you shift it. There's a different way of thinking about it. You can think of this beta as basically the bias term when you're computing the z's, and you can think of the gamma as a weight, a fixed weight, and that's just a different interpretation. But a nicer statistical interpretation is that you're moving it to the right location in the space. Did that answer your question, Alistair? Yeah, okay. So gamma and beta can be estimatable, right? So why do we need to scale by the variance? Again, you can think of the variance as a weight. This gamma as a weight. So this is no different than just having an additional learnable weight parameter. Okay. So here are the two steps of batch normalization. First, you normalize all the instances to have 0 mean and unit variance, and then shift them to the right position. So in fact, the shift can be thought of as this operation where the u's are multiplied by a weight gamma, and then a bias beta is added in. So out here, you don't need a bias because the bias is handled after the normalization. Is this picture making sense? Yes or no? Okay. So now This business of batch normalization messes up with how you compute derivatives. How so? Look at this. In your standard training, your loss was the average divergence over the mini batch, and the divergence for any instance didn't depend on the other instances, which is why when you computed the derivative of the divergence with respect to any parameter, you could just average the derivatives of the divergences for the individual training instances with respect to that parameter. You could just treat each independent training instance separately. But now, when you perform batch normalization, every instance is being normalized by the mean and the standard deviation of the mini batch, which means that if I change one of the other instances, that's going to change the mean and the standard deviation, and that's going to change this instance itself, which means that I can't be treating individual instances separately. I have to consider the batch as a whole because every instance affects every other instance within the mini batch. This making sense? Yes or no? Right. And so we'll see how. What really happens is that you have all the Z's of the mini batch go in, and then batch norm happens over the entire batch, and then every one of them is modified. But within this box, there's some computation which includes the computation of a mean parameter and a sigma squared. And every z influences this mean, and this mean influences every z hat. Every z influences the sigma, and the sigma influences every z hat. And so because of that, changing zb would change z1 hat. And so you can't just be computing the derivatives individually. You have to consider the derivatives of the entire batch as a function of the entire batch. Is that clear? Okay. So let's see how this works. But first, let's see how we can compute the derivatives until here. Until once the instances are normalized, all processing is local, right? Which means that I can compute the derivatives of the loss with respect to the UIs individually for each instance. And that is fine. And let's see how we do that, right? So here's what we had. This guy, Z hat, was gamma U plus B, right? So as I'm coming backwards, presumably backprop has given me the derivative of the loss with respect to Z hat. But then Z hat equals gamma U plus beta, right? So what is the derivative of the loss with respect to beta? Anybody? What is the derivative of the loss with respect to beta? So this relation tells you how U became a Z hat, right? Backpropagation gave you the derivative of the loss with respect to Z hat. So what is the derivative of the loss with respect to beta? Assuming that you have this guy. What is this? Anybody? What is it from this relationship? It's just going to be the derivative of the loss with respect to Z hat, right? Nothing changed. So we now have the derivative for this guy. This guy can be learned using gradient descent. What is the derivative of the loss with respect to gamma? What is dl over d gamma? What is this? Anybody? What is dl over d gamma? That's simply going to be dl over dz hat times u, right? And what is the derivative with respect to u? What is this guy? What is the derivative with respect to u? Come on, guys. It's going to be dl over dz hat times gamma. So this is easy, nothing complicated, very, very trivial. So here you have this. You can compute the derivative. Backpropagation will give you the derivative for z hat. Then from this formula, you can get the derivative for beta and gamma. The derivative for beta is simply the derivative of the loss with respect to z hat. The derivative for gamma is the derivative of the loss with respect to z hat times u over here. And so you can use these to estimate gamma and beta because you have the derivatives. And then taking a step back, the derivative for u is the derivative for z hat times gamma. This making sense to everybody so far? Yes, no? Okay, so very easy. So we've gotten all the way back here, and now we have the derivatives for these guys. We want to figure out how to go back from here and compute the derivatives with respect to the z's. That is the real challenge. And that's where you're likely to get tripped up. But then it's actually very trivial. And let's see how that will happen in the next, after this third poem. There are two questions here. One of you guys needs to mute yourself. Okay, 15 seconds. Five seconds. All right, let me stop this. Okay, answer to the first question. Is this first statement true? Okay, is the normalized value for any zi depends on all the zi's in the mini batch, right? And the normalized u depends on all the u's in the mini batch? False, okay. Batch norm is a vector operation over all the inputs in the mini batch, true or false? True, right? So the first statement and these are the answers. Okay, so let's go back and see how we can get the derivatives for these z's once you're given the loss derivatives for the u's. And now observe that every z influences every u. So when I want to compute the derivative for any zi, I have to sum over all of the u's. That the loss of the derivative of the loss with respect to any zi is the sum over all u's of the derivative of the loss with respect to u's times the derivative of u with respect to z. This clear? This must be obvious to all of you guys, right? Yes or no? So the challenge is, how do we compute these guys? Let's see. It looks very ugly, but it's not. So the derivative of the loss with respect to u is already computed. We must compute this for the derivative of every u with respect to every z. Now let's consider the through part. Say the derivative of a u with respect to its own z, right? Here is the entire influence graph. All of these z's influence mu. All of the z's and mu influence sigma squared. And for any given u, it's influenced by its own z, mu, and sigma squared. This picture making sense? This one here? The influence picture here? Yes or no? Okay, so once you draw the picture, the math becomes very easy. So the derivative of u with respect to z must sum over all incoming paths that connect z to u. So there's one path, which is this guy, which gives you the derivative of u with respect to z over this direct path. Plus, there's the second path, which goes from z to mu and mu to z, mu to u. So the derivative over this guy is the derivative of u with respect to mu times the derivative of mu with respect to z. And then there's the third path, which goes from z to sigma squared, but also from z to mu to sigma squared, and then finally from sigma squared to u. So the derivative here is the derivative of u with respect to sigma squared times the derivative of sigma squared with respect to z. This equation making sense over here? Yes or no? It's simple, right? Nothing fancy. So let's see how each of these is computed. Let's look at the first of these guys, derivative of u with respect to z. Now, that's the derivative over this edge. And that derivative is obtained from this relationship, right? U is simply obtained by normalizing z. So from this formula, and I'm speaking only of the derivative over this edge, what is the derivative of u with respect to z? From this formula, for this edge. It's
1 over square root of sigma,
square.
that thing, yes.
Okay, perfect. So we've already got this first term. Amazing. So let's put that in. Now let's look at the second guy, this one. This is the derivative of u with respect to mu, right? That too can be derived from this formula. What is the derivative of u with respect to mu? Anybody? It's from here, it's minus 1 over square root of sigma squared plus epsilon, right? So let me plug that in over here. Beautiful. Finally, what is the derivative of mu with respect to sigma? That's this with respect to z, that's over this edge. That's going to come from this relationship. What is the derivative of mu b with respect to any of the sigmas, any of the z's? Just 1 over b, right? So awesome. I can just replace that with a 1 over b. And so this guy is taken care of. So the first two terms have already been worked out. Is everybody with me so far? How have I computed the derivative? I still have a couple of terms to finish. Right. So what is the next term I must compute? Anyone? What is the next term I must compute? Derivative of u with respect to sigma squared, right? So what is this guy? This is what I want to compute the derivative for this edge. And what is that term? Anybody? That's going to come from this formula, right? What is the derivative? If I think of sigma squared as the variable, it's 1 over sigma squared raised to minus half. So someone help me. What is the derivative of u with respect to sigma squared? Standard calculus. There's going to be z minus b, right? Z minus mu times sigma squared plus epsilon. I'm having trouble writing with my mouse. Raised to minus half. That's the, oh my God, that's this formula. It's horrible. And so once you work through the derivative, that's simply going to be z minus b over 2 because you had a minus half times sigma squared plus b raised to minus 3 over 2. Everybody got this, correct? This clear to everybody? This is just your standard calculus from high school. Okay, so let me plug this over here. I've got this derivative. What remains now? What is the one term that remains? This guy, right? And to compute this, how do I compute the derivative of sigma squared with respect to z? I must sum over all incoming paths, right? So the derivative of sigma squared with respect to z is going to be the derivative over this edge, d sigma squared over dz, plus the derivative over this edge, which is d sigma squared over d mu times d mu over dz. This making sense to everybody? I'm using the same trick as before. Everybody with me? Okay, now what is this term? That's going to come from this guy here, right? So d sigma squared over dzi, what is it? This one. The 2 will come out, so it's going to be 2 over b zi minus mu b. This making sense to everybody? Yes, no? Okay, and so let me replace this first term. That's this one. And so now let's take the second term. What's the derivative of sigma squared with respect to b? That too is going to come from this formula. What is that going to be? Anyone? The sigma squared with respect to this one. What is the derivative of sigma squared with respect to mu? That's going to be 2 over b summation minus 2 over b summation z minus mu, right? There's a summation because I have to sum over all of these guys. This making sense? You can't lose the summation, right? What is this term? Summation z minus mu. Anybody? What does subtracting mu from z do?
Zero.
When I subtract mu from every z, what am I doing to the entire set? What am I doing, guys? Center it, right? So what does the summation become? Becomes 0. So that means this term becomes 0. Derivative of sigma squared over mu becomes 0, right? I can get rid of this is 0, I can get rid of this whole guy. And so the derivative of sigma squared with respect to z is just this term. And so now, so I can just replace that with the formula. And here's the crazy formula that you have for the derivative of u with respect to z. Now, how many of you think that this derivation was hard after what we just did? Was this hard or was this kind of, in retrospect, obvious? Once you drew the picture, was it still challenging? In retrospect, it's obvious, right? If I just gave you the formula, then it's not going to be obvious. But then once you draw the pictures and then you write everything out, saying the derivative must sum over all incoming paths, this is the only formula you're going to get. It's very nice. And so that's what you have. This is for the derivative for the through line, ui to zi. For I, this is dui over dzi, right? And now let's look for a cross line. Say duj with respect to dzi. What are the paths that you can see now? Anybody? What will, okay, let me do this for you. There's this incoming path, which is du over d mu times d mu over dz plus du over d sigma times d sigma over dz, right? And if you just work this out, this is similar for the I equals j term, but without the through term. And if you work it out, I'm not going to do this, but you can do this yourself. You're going to end up with this formula, and it's just as easy to get. It's going to be, the first term is the same. The second is minus of zi minus mu b times zj minus mu b divided by what we had before. And so here is the overall formula for the derivative of uj with respect to zi. When j equals I, we had this 3-term formula. When j is not equal to I, we had this 2-term formula. And so if I write the complete derivative of the loss of the mini batch with respect to any zi, I'd be summing over all the u's. And the terms I'd be summing is the derivative of the loss with respect to uj times duj over dzi. And we know that duj over dzi has this crazy looking, but actually very simply derived formula where you have these 3 terms when j equals I and only 2 terms when j is not equal to I. Plug them into this formula, and you get this even crazier looking formula that you could actually just write down on your own now that you know how to figure it out, right? And so here's the overall loss of the derivative. Here's the overall derivative of the loss with respect to z within any mini batch. It's the derivative of the loss with respect to the u divided by the standard deviation minus 1 over b times the standard deviation, the square root of the variance, times the sum over all instances in the mini batch of the derivative of the loss with respect to the u in the mini batch minus this third term. Okay, so I've got zi minus mu b in here, and I'm summing over all of the zij's. Again, I'm not going to explain the formula. We saw how this is derived. But then I want you to observe something about this. Let's say my mini batch consisted of a lot of instances which are identical. Then if all of the instances were identical, then d loss over duj is simply going to be d loss over du, because all of the instances are identical, right? You agree with this? Yes or no? Okay. What happens in that case over here to the second term? The second term becomes 1 over v square root of whatever times summation dl over du, where dl over du doesn't really depend on the index. This is 1 over b square root of whatever, sigma squared, times b times dl over du. So this b and this b will cancel out. And so this is simply going to be 1 over square root of sigma squared dl over du, right? That's what happened of the second term. Do you guys see this? Yes or no? Okay, so what would happen to this whole thing if the entire mini batch were identical? That whole thing is just going to become 0, right? So the first term disappears. What about the second term, this guy? Once again, dl over du is the same for all of the terms. So there's going to be some multiplicative term, which is this term, times dl over du, times, because this is no longer dependent on the index, times summation of z minus mu. And what is this term here? Summation of z minus mu? That's 0 also, right? So this term also becomes 0. Okay, so what did we find out? If the entire mini batch is identical, what happens to this loss? What happens to this derivative? If the mini batch consists of identical instances, what happens to this? Come on, guys. These canceled each other out and became 0, and this also became 0. So this simply becomes 0, which means by that point, the derivative here is 0. Any further back propagation is only going to see zeros. You're going to have no more derivatives to propagate backwards. That makes sense to everybody? And so here is a whole question. If I can get the polls out. Okay, 10 seconds, guys. All right, let me stop it here. So what do you think the answer is? It's true, right? Because the derivative of the loss with respect to this z becomes 0, at which point there are no more derivatives. There's nothing to back propagate. So if you perform batch normalization and your mini batch doesn't have sufficient variety, if all of the training instances in the mini batch are very similar, then the derivative of the loss with respect to the z's in the mini batch becomes so small that it basically becomes pointless. And it blocks further backpropagation. What do you mean by V similar, Shrikant? Oh, so you're asking me what this question here? Very similar. By very similar, I mean in terms of value. So if you have a bunch of training instances which are all very close to one another or identical, then batch normalization is going to block your derivatives. So you really want the mini batch to be diverse for batch normalization to be effective during training. Did that make sense? Yes, no, guys? Yeah. So Ayush, oh heck. The part, whenever I'm speaking of the derivative over one of the incoming paths, I use the partial term. If there's only one path between two variables, the partial and the full derivative are the same. Otherwise, they are partial derivatives because there are multiple incoming influences, and you can block one and keep the others, or make one non-zero and block the others. So those are partials. They will have a question about this in the quiz. Okay. But as far as we're concerned, they're just derivatives along individual paths. Now, batch normalization introduces a problem during inference. Batch normalization has this variable, the mean and the variance that depend on the batch. But when you're performing inferences, you only have one single training instance, right? If you have a single training instance, then what is the mean of that instance after it has been normalized? It's zero. What is the variance? It's zero. You cannot perform batch normalization if your batch is size 1. And so you need to have this mu and sigma squared as external variables somehow during inference time. And so what we will do is that once the model has been trained, you compute the means and variances of all of the mini batches in the data and compute the average mean of all the mini batches and the average variance of all of the mini batches. And this is what you will use to perform the normalization during inference. Did this make sense? This guy over here, that makes sense? Right. And typically, you're not actually going to perform this computation. You're going to keep maintaining a running average of the means and variances during training because you don't want to be performing additional passes through the data. And that's what you plug in over here. So batch normalization may be applied to some layers or to some selected neurons in a layer. You have all kinds of flexibility in how you use it. And it's shown to improve both convergence rate and the performance of the network, the generalization of the network. And as it turns out, batch normalization conflicts with dropout, which we will talk about next. And so that tends to be an issue. To get maximum benefit from batch normalization, learning rates must typically be increased, and the learning rate decay must be faster because you're going to get greater derivatives. And you also need better randomization of the training data order because if you don't, then the batch normalization can actually block derivatives. And so here was the first paper on batch norm by Sergeyev and Zegedy, 2015. They show this was on, I think, I don't remember this was which data it was, maybe I missed. This dotted line shows the usual training curve. And then when they use batch norm, you can see how it gets the same performance and even better, much quicker. Batch normalization can actually speed up training and give you more generalized models, orders of magnitude faster than if you do things without batch norm. And so to add to the lessons we've seen so far, covariate shift between training mini batches may cause problems and may be handled by batch normalization. So any questions so far? Any questions? Okay. So I did actually also make some claims which might not entirely be true. We said we attempt to learn an entire function from just a few snapshots of the function, some input-output pairs, right? So, and the way we did it was that the current function network gave you some function, the desired output gave you a different function, and you defined a divergence between the desired and the actual outputs of the network at these training instances, and you try to minimize this average divergence, which is L2 or KL, right? And I've just shown the squared error over here. But then you're hoping that when you minimize the error at these training instances, you will actually also minimize the error everywhere else, but that may not happen. There's nothing stopping your algorithm. The training data will only comprise these red dots, the instances shown by these red lines, right? Input output pairs. And the hope is that you end up learning this dotted line, which is the actual function you want. But there's absolutely nothing stopping the network, the algorithm, from learning the orange curve. So is this making sense? What's happening here? And so somehow we need to prevent this, right? How do we prevent this? We need additional smoothing constraints that will somehow fill in these missing regions in an acceptable manner. To give you a better idea, let's consider a simple network which is performing binary classification of scalar data. So if these reds and blues are your training data, ideally what you'd want is a curve of this kind, like the blue curve, right? Where you say that here things are confused, but out on the edges, they are more deterministic. But because a network of this kind has so much capacity, there's nothing stopping it from learning the purple curve. Is this making sense? Right. And so you want to prevent this. Now, why is it possible for the network to learn this purple curve? That's because the network is able to learn these really sharp rises and falls. And that has to do with the activation function we use. Let's say I was using a sigmoid activation function. A sigmoid activation function has this property, it has this formula 1 over 1 plus e raised to minus wx. If w is a parameter, right? If w is allowed to increase in an unbounded manner, when w is infinity, a sigmoid simply becomes a threshold, like so. If w is very large, it's still going to end up looking something that's very close to a threshold. It's a smooth function only when w is bounded in value. This making sense over here? And so, because of this, if the sigmoid is allowed to rise in an unconstrained manner, this is true of any activation function, now the individual neurons are now able to rise and fall very sharply. And that enables learning of this kind of a function, which doesn't make a lot of sense. So how would we ensure that it's this function you learn and not the crazy red curve? How would you ensure that? Anybody? Prevent the magnitude of W from becoming too big, right? You want to constrain the weights to be low, which will force slower perceptrons and smoother output response. And how do you force the weights to be low? So here's your standard loss. The standard loss was just the average divergence over all of the training instances in the network. The W's are the network parameters. In your conventional training, you're just going to minimize this loss. But now they're going to add an additional constraint. You're going to add this extra constraint which says that not only do I want the average divergence to be minimized, I want this to happen while also ensuring that the weights themselves do not get very large. So you add this extra regularization term, which minimizes the weights in addition so that the overall loss function not only minimizes the divergence, while doing so, it also minimizes the weights. Is this making sense to everybody? And this lambda over here tells you how important it is for the weights to be minimized. The larger the lambda is, the more the network is going to focus on ensuring that the weights are small. This half over here is just a convenience factor because you're using the squared norm. And now, when I perform gradient descent, I'm going to be performing gradient descent using this modified loss function, which also has the squared norm of the weight. So here's what we have. The new loss is the average divergence plus half of the lambda times half of the squared norm of the weights. So when I take the derivative of this loss with respect to any weight, you get the usual divergence term, the usual loss term, which is the average of the derivatives of the divergence with respect to the loss, plus lambda times the derivative of this guy with respect to W, which is going to be, the 2 comes out, 2 and 2 cancel out, lambda times WK. So is this making sense? This is just a straightforward calculus, which came from here. This making sense? And so this is the term that you're going to plug in to your, gradient descent. This is the average over the mini batch, right? So instead of T, this is the mini batch size. If I use this derivative term in my gradient descent, so I'm going to say WK is updated to WK minus eta times this derivative, which is WK minus eta times this first term, which is the average divergence derivative, minus eta times the second term, which is eta times lambda times WK. So is this formula making sense here? I can combine these two terms. I can combine this guy here and this guy and write it as 1 minus eta lambda W minus eta times 1 over B summation law. That's what this becomes, right? So yeah, that's right, Shrikant. So is this making sense? What we just got. You'll have to pardon my handwriting. It's being done with a horrible mouse, right? And now I don't need to write eta times lambda. I can just combine those into a single term lambda. And so here is the updated learning rule. When you use the regularization of the W's, you actually multiply the weight by a scaling factor that shrinks it, because as lambda becomes, for any value of lambda between 0 and 1, this becomes a number that's less than 1. So this is your, what did we call it? What did we call that, guys? Someone gave me the term for it. Not just regularization, weight decay, right? You decay the current value of the weights before taking a step. So what weight decay is really doing is basically adding this extra regularization term that ensures that the weights are, in fact, also maintained small. So is this making sense? What we've covered so far? Mm-hmm. So keeping weights low also ensures that the slope of the ReLUs stays bounded. Otherwise, you can think of the ReLU, the actual slope of the ReLU is scaled by the weights. If the weights become infinity, the ReLU is going to become a right angle, which you do not want. So in every case, regardless of activation, you want the weight to be small. Does that answer your Anai? Yeah, I assume it does, right? So here's how this modifies your update rule. This is exactly the same mini batch update pseudocode as before, except now you're actually multiplying the weights by a 1 minus lambda factor before the update. Here's another way in which you can try to make sure that the function that is learned is smooth. Now, in a deep network, every layer operates on the output of the previous network. So the layers, if the layers enhance the slope, then as you go through the network, the function is going to get steeper and steeper. On the other hand, if the layers are all regularized, every layer is going to operate on a function that's been smoothed by the previous layers. And so as you make the layers deeper, the function gets smoother and smoother and smoother. So for a given number of parameters, deeper networks impose more smoothness than shallow ones. Here's an example. Here, this was a simple classifier where we're trying to learn these two decision boundaries from 1,000 training data points. And we've used every possible training trick except actually every possible training trick. We even had weight regularization, weight decay. And it ends up learning these completely hideous decision boundaries if I just have a shallow network. But then, if I take the same network with 660 neurons, here's a decision boundary. If I arrange the 660 neurons in 3 layers, here's the of 220. Here's the decision boundary it learns. This is 4 layers of 115. Here's the decision boundary it learns. This is 6 layers of 110. This is what it learns. 11 layers of 60. This is what it learns. So you see what happens over here, the same number of neurons. If I rearrange them to be deep, the deep network has implicit smoothness constraints that learns a better decision boundary than the shallow ones. This making sense? Exactly, Shrikant. So is this making sense, guys? There's another way of doing it. Just having lots and lots of training data also helps to smooth. But this is a nice principle to keep in mind. So to add to our lessons, data under specification can result in overfitted models and must be handled by regularization and more constrained, generally deeper network architectures. There have also been other techniques proposed to improve the smoothness of that learned function, like L1 regularization, regularizing with added noise. But possibly the most influential method has been dropout. And before we talk about dropout, it's useful to talk about another technique, bagging, which has been popular in the machine learning community for a very long time. This was popularized by Leo Breiman. And the idea in bagging is that given some training data samples, you sample the training data and derive several different subsets and learn many classifiers from all of these subsets. And then the eventual classifier that you compute simply averages the decisions of all of the individual classifiers learned from the various subsets. And this is known to give us a much more robust classifier than simply training a single classifier on the entire training data. So keep that in mind. That's bagging, right? Now, what do we do in dropout? In dropout, during training, for each input at each iteration, we're going to flip a coin. And with a probability of heads, alpha. And if the coin turns up tails, you're going to flip it at each neuron. And if the coin turns up tails, you're going to switch the neuron off. So for example, this might be your network, and the coin turned up tails for these neurons and these and this and this and this. So all of these neurons are switched off. And this is the remaining network that you would use to process X1. You're going to do that. So basically, you have effectively turned all of these black neurons off. Now, flipping a coin can be done computationally through a Bernoulli random number generators with success probability alpha. But did this make sense, what we just did over here? Yes or no? Okay. And you're going to do it differently each time. So the first input might see this network. The second input might see a completely different network. The third input might see yet another network. And because you do it afresh each time, the next time you process X1 might see a completely different network because you're going to keep flipping the coin every time you pick a training instance, regardless of whether you've seen it before or not. So what happens is that eventually So each neuron sees a different network, and the forward pass inference is done over a different network for each neuron. And the back propagation is also done over the reduced network seen by each neuron. So how many such different networks can I get if I have n neurons in my overall network? How many such networks can I get? Anybody? 2 raised to n, because every neuron can be switched off with a, can either be switched off or on. So for a network with n neurons, there are 2 raised to n possible subnetworks obtained by choosing different subsets of nodes. So effectively, this is like bagging. You start with a network, but then you implicitly compose 2 raised to n different networks simply by turning different neurons on and off. And for each training instance, you randomly pick one of these 2 raised to n networks and use this. So this is just bagging. That makes sense? You have 2 raised to n classifiers. Each instance is training a different classifier. Yes or no? That makes sense, right? Now, that's one interpretation of dropout, but there's another interpretation. Dropout can also be thought of as a mechanism to increase pattern density. So let's say I have a deep network of this kind. But if I don't have constraints, then there's nothing stopping one particular layer from simply learning a pass-through function where it sets all the cross weights to close to 0 and the direct weight to 1. And this effectively loses a full layer in the network, and this happens all the time. Do you see what's happening here? Yes, no? This can happen. Yes or no, guys? And so I see a single yes. Maybe you give me a few more yeses and then I'll continue. Okay. So what dropout does is that every now and then, this neuron is going to get switched off. If this neuron gets switched off, this guy can no longer just look at this one. It's forced to look at neurons on the side. And so dropout forces the network to learn dense weights as opposed to learning these sparse weights, which just act as pass-through functions. And so it ensures that you're making maximum utilization of all of your layers. That makes sense? Yes, no? Okay. So how do you actually implement dropout? During the forward pass, at each neuron, you compute a mask, which is a coin flip by generating a random number from using a Bernoulli random number generator with probability alpha. And then the actual output is multiplied by the mask, which decides whether that output is floored or it's actually used. So during the backward pass, you do the same thing. After you compute the derivatives are multiplied by the same mask, so that neurons which were switched off no longer pass any derivatives backwards. That's it. So dropout effectively trains 2 raised to n networks. But then, continuing the bagging principle, what did we do when we were bagging a lot of neurons, classifiers? We computed the average of all of the classifiers. In other words, you want to compute the expectation over all of the 2 raised to n networks when you compute your actual output. This is what bagging would do. Is this making sense? Number one. Number two, is this feasible? A, is this making sense, guys? That this is what you want to do. You're effectively learning 2 raised to n networks and you want to average over all of them. This is what you want to do, but it's not feasible, right? So then you make an approximation. The network is a function of many y's, where the y's are the individual neurons. So you say that the expectation of the network of y's can be approximated as the network of the expectation of y's. Is this making sense? That this is an approximation? And would this be true? in general? Is an expectation of a function the same as the function of an expectation? Is the average of x squared the same as the square of the average of x? It's not, right? So this is not going to be true. Almost certainly never going to be true. Nonetheless, we're going to use this approximation because it makes things feasible. Okay? And so what this means is that we're still going to use the full network, except that at each neuron, instead of using the neuron directly, you're going to take the expected value of the neuron. Now, what is the neuron? Every neuron is being switched on or off using with a Bernoulli variable whose probability of success is alpha. So the expected value of the neuron is simply the output of the neuron multiplied by alpha, because alpha is the fraction of times that neuron is going to be on. And so this is the expected value of the individual neurons. Right? So Shiva, this approximation is always, except in the for linear functions, that approximation is always a very strong, it's a very poor approximation. We just use it. Think of this, right? The average of x squared is not equal to the average of x squared. If x was a Gaussian random variable, this is a positive, this is the variance, but this is going to be 0, right? So it's always a poor approximation, but we use it. And is this formula making sense to you guys? Yes or no? I'd like to see a few more yeses. Alpha is the probability with which the neurons were switched on or off. So alpha is the probability that the neuron was retained on. 1 minus alpha is the probability that it was switched off during training. So what this means is that during inference, every y is simply going to be replaced by alpha times sigma, where sigma is the activation. Alternately, you can redo the math and say that all the weights are multiplied by alpha. And this too is going to give you the same thing. So after you train your network using dropout, you'd scale the weights up by the dropout factor. This is your inference code. In the usual inference, you just say y equals f of z. Now you'd say y equals alpha times f of z. That's the only change that happens. You can also do something else. During training, you can pre-multiply the activations by alpha inverse and just use the network as is during inference. And this too is equivalent. So here was the first paper on dropout by Nitish Srivastava et al. In 2013. And this was again, I think, on MNIST. They show how the classification error without dropout saturates at around 1.6. But then once you use dropout, the thing falls really fast and continues to fall beyond 100,000 updates of the parameters. Right. So you're not using dropout during inference, Pranav. For dropout to make sense, you have to take the expectation over all 2 raised to n classifiers that the dropout effectively learned. And so if you want to take the expectation over all 2 raised to n classifiers, it's not feasible. So instead, you'd compute the network over the expectation of the individual neurons. That's all. That makes sense? Right. So that's what we do, right? And there are many variations on dropout. Yes, there are, but we can discuss this after class. I'm running out of time. So there are many variations called zone out, drop connect, shake out, white out. They're variations on the same basic principle and are based on the same concept. So to add to our lessons, dropout is a stochastic data or model erasure method that sometimes forces the network to learn more robust models. Now, to close out, a few other heuristics that you often use during training. Early stopping. The model is being learned to optimize performance on training data, but that doesn't mean it's going to generalize to test data. So one of the things we often do is to keep testing your models on validation data. And whenever the performance and validation data begins to increase, you realize that you're beginning to overfit to training data at that point and stop training at that point. So that's early stopping. Another thing that you do is to try to not accept derivatives when the divergence derivative is too high. Your loss function can sometimes be very steep with respect to some variables. So if you compute the derivative, that can become so large that it makes training unstable. So we use gradient clipping. You set a ceiling on the derivative value, typically 5. If it exceeds that, you set the threshold to 5. Another thing that we often do is to create synthetic data by simply distorting your training examples in a variety of ways. For example, if you're learning an image classifier, you could rotate and flip your image, and it's going to remain the same class. And so these synthetic training data instances can also be used. It's called data augmentation. And there are other tricks like normalizing the input, basically making the entire training data zero mean unit variance, various initialization techniques, and so on. Eventually practice makes a man perfect. Many of these things can only be learned empirically. And so, just to close out, when you set up a training problem, here's what we do. We obtain some training data using appropriate representation for inputs and outputs. Choose a network architecture. More neurons need more data. Deep is better, but harder to train. Choose the appropriate divergence function. Choose the regularization. Choose heuristics, batch, norm, dropout, etc. Choose your optimizer, for example, Adam. Perform a grid search for other hyperparameters like learning rate, and then train. And evaluate periodically and validation data for early stopping if required. So in closing, over the past few lectures, we've outlined the process of training neural networks with some history, a variety of algorithms. We've looked at gradient descent-based techniques, regularization for the generalization, algorithms for convergence, and some heuristics. But eventually, you're only going to learn through practice. Practice makes you perfect. So I'll stop right here. Thank you all for